Yeah, last week was the introduction week, and we've talked about the general usage of Matlab, some toolboxes. Starting from this week on, we will get more and more involved in control system design. And today's topic will be about the basics that are necessary in this lesson in the laboratory sessions, or even in the theoretical part. Now, the prerequisites are basically the root locus plot. You should be familiar with them. And then there are also the body graphs, which is basically the second part of our course throughout the semester. And then there's also a neat example about impulse step and ramp responses. Now, as you can see, and as you might know, it's not that hard to plot a root locus plot, for example, using Matlab, or acquire the body plot of a certain transfer function. You can use the control system toolbox, and there are just the rlocus and body commands. But what we will examine today is basically what they mean and how we can re-implement them using the symbolic toolbox. So yeah, and the first one is root locus, so let's start with that. Now, since we will be using the symbolic toolbox, and since we will define transfer functions using both the symbolic toolbox and the control system toolbox, let me show you how I personally define the transfer functions and how do I indicate which toolbox is used, basically. So our Laplace domain variable S will always be defined with using the symbolic toolbox. And if I, for example, define a certain transfer function that is symbolic, what I'm going to do is I'm going to use an extra S here. So, for example, if I'm going to define 1 divided by S plus 1, this is a symbolic expression. This is not even a transfer function object, just a symbolic fraction. But if I use, for example, a TF object, I will use just a single S in order to separate them. So if you see this, this is probably a symbolic variable. And if you see this, this is probably a transfer function object. So now you can define the transfer function using line 6. And what you can do is you can call rlocus, and it will automatically generate you the root locus plot that you're interested in. But first of all, what is the root locus plot? And second of all, how can we plot it on our own? So any ideas? What does it mean? Let's start with that. Why do I need a root locus plot? So why is this necessary? Any comments? So feel free to just answer. It doesn't have to be correct. You can just try your best. So anyone? Okay. Well, the root locus plot is the most basic method in designing a controller. And the controller is the most simplest controller you can find. Namely, it's a static gain. So we are looking for a static gain controller. What does that mean? Well, we have a feedback structure. If we try to implement a controller, we're talking about closed loop control. Therefore, we need a closed loop structure. So let's have a controller, fs, transfer function. And then there's also the system. Of course, we call this the reference, and then we have this summation point, which generates us the error signal that we are interested in. And the job of the controller is to use this error signal in order to generate the ideal input that is necessary for the system in order to track the input. So what we want to see is we want to see that the output follows the input, or the reference in this case. So therefore, we have also this feedback, which I might try to depict like this. So like this. Of course, here's a minus sign, but I'm not able to show that here. Now, the thing is that we need a sensor, a measurement of the output. We feed it back, so we take the output compared to the reference, and the difference between the reference and the output is basically error, and this should go to 0. So this should basically be a signal that ends up being equal to 0, because in that case, r minus y should be equal to 0. So the output is basically the input reference. There's no difference between them. Of course, this is not possible initially because there will be a difference. If, for example, the system has no input, then the output of the system will be 0. And if I have a certain reference, the difference will not be equal to 0. So we try to come up with a controller that tries to make this error stable, or in other words, it forces this error to become 0. So if that's the case, then we have a control signal, we apply that to the system, and then we observe the output. So the most simplest controller, of course, the most simplest in my mind would be basically U equals E. So 1 times E, basically, because there's not even a gain. The error is directly fed to the system as an input, but this might not work always. So a static controller, a static gain here in this case, is the so-called p-type controller. And this P stands for proportional, because the relation between the error and the control signal is proportional. So we have this gain, and we're looking for this gain. Now, if we have such a feedback structure, then I need to work out what the closed loop transfer function looks like, because before I've used a controller, I have just the system, the plant on its own. And this plant has a certain characteristic or behavior to it. But now I want to change that behavior in some sense so that I achieve my goal. Now, this means that if I use a controller and have a feedback structure like this, the plant is not the system anymore. The system that I'm looking at is the feedback structure. So what is the transfer function of the closed loop shown here? So if you're not really good at this, you might also use the relations here. For example, we have one of them is written down, or let's generalize it like this. So U is equal to Fs times E. So this is one equation. And then we have Y equals GSU. This is another equation. And then we have also R is equal to, E is equal to R minus Y. Now, and the goal here is to find a relation between Y and R. Since the input is R and the output is Y, so the relation between them is basically our closed loop transfer function. So you can use these here and try to come up with this relation. And if you do that, what you will get is you will get the following. You will have Fs times Gs divided by 1 plus Fs times Gs. So this will be what you will find out of these relations here. Now, yeah, this transfer function needs some attention, and since our controller Fs is equal to k, a certain static gain, let's plug that in too. So this means that k times gs divided by 1 plus k times gs would be the closed loop transfer function here. So let's call this ts, by the way. And let's look at the relation or the transfer function, how it looks like. Let me get rid of these here. So I have defined the Therefore, I need to change it like this because I'm in the symbolic toolbox, basically. So I have the open loop transfer function, the plant, GSS. I need a certain static gain, K, and then I have this relation. So K is missing, so let me define it too. This is also symbolic. And then we will end up with TSS. So let's run the script for once. And yeah, the symbolic toolbox is a bit interesting because it doesn't give you the result that you're expecting most of the time. This is not really useful because if I write it down myself, I would probably write this down. So let me show you how it looks like in a more human readable form. It would look like this. So this is basically K divided by, and then K divided by S plus 1 times S plus 1, something like that. So this is not really that useful because there's calculations to be done. In order to do that, you might go ahead and say, I have a certain expression. This is a little bit complicated. So let me simplify it. If you use simplify, then the symbolic toolbox calculates a better form or a simpler form for you. So now this looks a little bit better. And this also shows me that there's a certain case that I might end up in trouble because I have K divided by K plus S plus 1, or in other words, S plus K plus 1. And since this is a simple transfer function, a first order transfer function, I can immediately see where the pole will be placed, because the denominator here is the characteristic polynomial that I'm after if I'm looking for poles. Now, if I equate this to 0 and find a solution for S, this would be -1 minus K. Now, usually, if you are dealing with systems in real-world examples, for example, then what you will see is that most of the systems in nature are practically stable. If you give it some energy, a limited one, then the output will be limited. And it will probably be lesser than your input energy. So what this means is that there's some dissipation going on. So this means that you would have stable systems. But if you are designing a controller, then you might end up in unstable systems, in unstable closed loop systems. So how is this possible? The definition of stability is that all the poles should be on the left half plane. If that's the case, then you have a stable system. If it's on the j omega axis, then you have marginal stability. If it's on the right half plane, then it's unstable. Now, in this case, I can choose K so that the pole is placed on the right half plane. For example, if I take K equals -2, then the pole would be at 1, and the system will become unstable. So designing a controller needs a bit of attention in terms of stability. That's the first step. But most of the time, the designs are not limited to stable closed loops. Sometimes you have some requirements of closed loop systems. For example, I want to have a certain settling time, a speed of response. I want to have certain frequency behaviors. So there are more limitations to designing a controller. But since this is a basic controller, a p-type controller, a static gain, the first step for me is to try to get an interval, at least, for the controller parameter K, so that I will always end up in stable closed loops. So this is one thing. The other thing would be then also to place the poles with a strategy that serves a certain purpose. Now, if I choose a pole distribution that has a certain settling time or overshoot properties, that would also be nice. So that would be the second step. For today, and for the sake of introduction and simplicity, we will stick to the stability part, but that's not all of it. So now I can see that there might be problems with stability if I have a certain controller and a closed loop system. I want to plot the root locus plot because that helps to understand how the system will behave, because what I'm really doing is I'm having a parameter. I'm changing that parameter over an interval. And what I get is I get the position of the poles. So they will move around on the S domain, and I will get a certain position. And it will tell me when they pass the j omega axis, because that's the danger point. So if I'm passing it, then I will have some unstable poles. So therefore, we need a root locus plot. Now, in the classical sense, if you have, for example, pen and paper, and you're in an exam, what you will do is you will follow some certain rules to plot a root locus plot. But that's not about it here. What we want to do is we want to use the computational power of Matlab, and we don't want to go through the rules of plotting the root locus plot by hand. Now, yeah, we have basically a hint here in line 15 and 16 on how to accomplish this plotting of root locus. So what we can do is we can try to plug in some k values if we get the characteristic polynomial of the closed loop system. We can use an interval for k, plug in the values of k. For example, what I can do is, let me first acquire the characteristic polynomial. Let's call it PCS, polynomial characteristic, and the s variable here. So in order to do that, I have to use this fraction, and I need to decompose them into its numerator and denominator, and take the denominator part. Therefore, we have a command in the symbolic toolbox, nom_den, and we will take basically the numerator and denominator. So I need the denominator. I don't really care about the numerator here. Let me place a semicolon here. So we have k plus s plus 1. So at this exact same point, what I can do is I can choose between two separate approaches. One of them is to use the coefficients of this polynomial in order to calculate what the poles are. And the other one is to equate this to 0, solve for s, and then plug in k, so I get again the positions of the poles. So let's for now use the coefficient method. So let me try to calculate the coefficients of the denominator. So I have talked about this. If I have a denominator that looks like this, k plus s plus 1, and if I use this clef function like in line 11, what will happen is that the symbolic toolbox will not differentiate between the symbolic variables, because if you look at line 3 and line 6, what you can see is we have two different symbolic variables, and the symbolic engine does not care about which one has privilege or if it's having a certain meaning to you. It just treats them as equal, and it gives you the coefficients. And then there's also the constant term. So that's the reason why you have 1, 1, and 1. In order to solve this, you can tell the symbolic toolbox that you are interested in a certain symbolic variable. And you can see that it changes strategy. It gives you k plus 1 and 1. But in order to be safe, what we will also provide is we will provide a character vector here called all, which means that if there are missing s powers of s, for example, if you have s squared plus 1, then you don't have any s term. So you are telling the symbolic toolbox to also fill in the missing powers. If it's 0, then you should give me a 0. Because if you don't do that, and if you, for example, give s squared plus 1, so let me get rid of this. So what you can see is that this one here can also be s plus 1, because I immediately associate their positions to a certain power of s. Therefore, I can reconstruct a polynomial out of a vector. But this is the actual vector that I should be looking at if I'm doing such a thing. If I don't, then it doesn't really matter, but we will associate vectors to certain s powers. And the reason behind that is basically the TF function that we will use in the control system toolbox, because I will provide a numerator vector corresponding to all the powers of s as a vector, and then a denominator vector, which is the same. So if I'm missing certain powers, then I will mess up my transfer function. So therefore, it is important to us to use the line 11 here. So yeah, let's get back to our code here. Now this is a coefficient vector, and it looks like this. So s plus k plus 1. So at this point, what I really need to do in order to emulate the process of plotting a root locus plot is that I need to plug in some k values. And since I have a k already defined, I should not, or I should avoid using k again, because if I define something like this, then I will lose this implementation here, and I will mix up the value and the actual symbolic variable. So in order to prevent that, I can use kval, which stands for the value of k, or which is a placeholder here, or kvec, so I will specify what it really is. So let's have a kvec, a vector for the symbolic variable k, that will be plugged in later. And let's start with simple values. Let's have 3 different k values. Now I need to choose each element of this vector, plug it in, get a certain solution, and plot it on a figure. So you can always use this approach here, or rather this one here. So this is basically a for each loop here instead of a for loop. But I'll skip that, and I will always use the element by element for loop. And the reason behind that is to be in a specific standard, because there might be cases where we have 2 equally sized vectors, and I'm reading one and writing to the other one. So I need to use elements in that case. So feel free to use whatever you want, what you would like, but I'll be using this one here. So this means that at each iteration, I will have a certain k value that will be extracted from the ith element of the k vector here. And what I need to do is I need to use this coef variable here, plug in k into kval, and then go on from that. So let's say a temporary variable should be equal to subs, because subs is the substitute function here. If you don't know or don't remember what it is, you can always use help, and it will show you what it means briefly. And as you can see, the usage here is to provide a symbolic expression, provide a old variable or an old expression, and then the new value that should be plugged in into old in S. So therefore, our old expression is the coefficient vector that we've calculated here. Our old symbolic variable is k, because we want to plug in into k, and then we have kval. So if we do this and see what the outcome is, you can see that there are 3 values here. And what you also can see is that it is basically symbolic here. If it would have been a double variable that we use in Matlab, it would look like this. But instead of that, we have the fractions, which means that we are still in the symbolic toolbox. Now, if we have a, let's for simplicity convert it into double to avoid problems. Because at this point, it doesn't really matter if I have this vector or if I have the double version of this, because there's no unknown. And if there's no unknown, then I can directly use the double version of it, so the numeric version. So we're practically doing that. If I run this, I get this. Now, what's left is that I need to calculate the roots of this polynomial coefficient vector, because what this means is that I have s plus 1.1, and then the second one is 1.2, and the next one is 1.3, which is expected. So if I have a vector that corresponds to the coefficients of a polynomial, then I can use this function roots, which accepts a vector and calculates the poles. Let's call this poles. So this is one way of doing it. The other way would be to use the expression itself, plug in k, and then equate it to 0, or use the solve function here. So if I run this, you can see now that I have the corresponding poles. The only thing that is left is I should plot them on a certain graphic. Now, let's do that. Before I start this for loop, I'm going to create a figure. And throughout this course, what I'm going to do is I'm going to write this line over and over again. So I will call CLF, which stands for clear figure. So I've created a figure, or I've chosen the one that's already created. It doesn't have to be always creating it from scratch. So I'm clearing it, therefore, because I'm not sure if it's already newly created or if it's an old one. And then I open up the hold on flag, which means that each plot should overwrite the previous ones. If I don't do this, plot will erase the plot and then only show the last plot, basically. And for reading aid, I will include grid on. And that's basically it. So you can also have some customization here. This means that I will have, for example, the real part as the x-axis, and the y-axis should be basically the imaginary part. You can call this also sigma and j omega. It depends on what you really want to do. And an interesting thing about Matlab is that it has some LaTeX support. And if you're familiar with what LaTeX is, it's basically a coding language that generates academic papers or PDFs. So if you have certain symbols, what you can do is you can, for example, use sigma and omega, and a backslash here helps you in creating the actual symbol here. But it's not really that important. Just let me remind you if you know what I'm talking about. So once I've created this plot, I will use the plot function. And the plot function expects from me a vector for the x-axis coordinates and a vector for the y-axis coordinates. So there should be two vectors. And if you have, for example, a point 1, 1, and let's have also 2, 3, then what plot expects is that you should, let me change this too. You should provide 1 and 2 as a separate vector, and then 4 and 3 as another vector. So you should use plot for plotting a line between these 2 points here. So the x-axis are in a vector and the y-axis are in another vector. So therefore, if I want to plot the poles on a plot, I need to get the real parts because that's associated with the x-axis. Therefore, I need to calculate it. That would look like this. And I need to calculate the imaginary parts because poles will have complex valued numbers in it, or complex numbers in it. So a complex number has a real part and an imaginary part, x-axis and y-axis. So yeah, I can also provide a certain decoration property argument list here. For example, if you provide line width to it, it will have a thicker line. You can also give it a color, for example, red, or you can specifically tell that you're telling plot that you are providing a color. You can also use an RGB vector here, but it should be scaled down to an interval between 0 and 1. So 1, 0, 0 would be again red. So there are customizations, and if you're interested in it, you can just call docplot. It will give you the documentation of plot. Opens up a new vector, a new window here, and you will see the detailed documentation. Help plot also helps you out, but it does not go into detail. If you want to have some detail and These are called line spec here. What you can do is you can click on line spec, click again, and you have some line style markers, some colors that are already predefined. And lots of stuff that you can customize in your plot. So if you are experimenting with this, I highly recommend you to use the documentation. And by the way, if you Google something like this, if you Google Matlab plot, then you will end up in this page because this is the documentation page of Matlab. So now let's omit all this here. Maybe the line width can stay because it is sometimes hard to see here. So now an interesting fact, and you can, by the way, see that on the omega axis we have j omega, and in the x-axis we have a sigma here that was accomplished by using this backslash sigma backslash omega. So if it's if it's from the Greek alphabet, you can just assume that you can use the name here, you can use nabla, mu, whatever. So yeah, but you can see, even though I have used this plot here in line 20, it didn't generate what I was expecting it to generate. So is there a problem here? Because we've called plot, we've provided the real and imaginary parts, but we didn't end up in a graph. It's an empty graph. So why is this? Well, the reason is that the plot function on its own expects at least two elements, because its default is to plot lines, and a line consists of two coordinates at least. So therefore, we have only provided just one coordinate here, the x value and the y value of it. So it didn't generate any plot. But you can overcome that by telling, for example, the plot that each coordinate we should plot a cross, for example, or use a cross marker for each point and then connect them. So that way we will end up in the following. As you can see, we have now crosses or X's here. By the way, this is a marker, so you can also tell plot to use marker. It's basically the same. But there's a version of argument list where you can just use the third argument as marker, color, and line type, line spec. So this is therefore also possible. You cannot put this somewhere here. It should throw an error. The position of this, if it's not, then you should use marker, color, or line spec, etc. So now we have basically, tabii ki.
Az önce grafiği neden çizmediğini anlamadım. Yani x koordinatı ve y koordinatı vermiş olduk aslında.
Evet.
Yani sırayla üçer tane x ve y koordinatı verdiğimizde çizmesi gerekmiyor muydu?
Üçer tane verdik mi peki? Üçer tane vermedik ki. For loop'una, for döngüsüne girdiğinde bir tane var. Çünkü bir tane birinci dereceden bir sistem. Kapalı çevrimi. O yüzden bir tane kutup buluyor ve bir tane koordinat vermiş oluyor. Şöyle oluyor yani. İlk 0,1'i alıyor. 0,1'i burada birinci elemanı alıyor. Birinci elemanı aldığında 0,1 geliyor. 0,1'i yerine yazıyor. Çıkan kutup bir tane. O yüzden de bir pozisyonla bir çizgi çizemiyor. 2 tane lazım minimum. Ama ikinci dereceden olsaydı çizerdi muhtemelen.
Anladım.
So the question was about the fact that we've provided 3 values as a vector here. Why didn't it plot a line? Because it has 3 coordinates. And the answer is that we have 3 values. That's correct. But we have a vector and we loop through this vector element by element. So at each iteration, we have only one element. Therefore, since this is a first order transfer function, we have only one pole, and one pole results in one coordinate, not 2. So therefore, we have to put in a marker here, x. So now we have a certain way of plotting it. Let's increase the interval here, and let's see what happens. Now, you could argue that this does not really look like a root locus plot, and you would be right. And even if I would increase this interval a bit more, it will not really change because it consists of just points. I'm not really connecting them. If you use the rlocus command, it has lines in it. So I don't really have this here. I'm just placing dots here. Before I transition into drawing lines, let me increase the order of the open loop system here. So let's make it a s squared plus 2 times s plus 1, for example. Or maybe a different one. Let's make it 4 or 3. So now, maybe we should just use 2 real values, like s plus 1 times s plus 2. So we know the starting positions. So this means that at -1, we should have a open loop pole, and then at -2, we should also have another one. And they will approach this point here, which is the midpoint. They will coincide, and then one will go tend to j omega or infinity, and the other one would approach negative infinity. But again, we have 2 poles here. Let's increase it even further. Let's have also times s, which means that we are adding 1 pole at the origin. Now this looks more like a root locus plot that we would expect, but there's a difference. And the difference being that we don't draw any lines, we have just dots, basically. So can I, for example, color each branch a different color? Because that's also a convenient thing in the root locus plot. So how can I do that? Well, I need to know the order of the transfer function that I'm providing, but let's, for example, fix it here. It is a third order transfer function, therefore we will choose each pole on its own. Let's call J here. And what I can do is I can basically also define a vector, a color vector here. Now, if you want to define a color vector, what you can do is you can basically, for example, for red, you can provide RGB values like this, 0. And let me also define green, and maybe also blue. So now this is basically a matrix. This is not a vector, this is a matrix. And each row is a color. So therefore, what I'm going to do is I'm going to access this, change the color here. And I need to choose the corresponding row and all the columns. So the ith row, or jth row in this case, and all the columns. So this should take always the first pole and give it the red color, take always the second one, give it the green, and the third one blue. And we have a semicolon here. So there we go. This looks a bit better. Now I can trace the pole, so I can see which one went where and what's really happening. So the last thing would be to draw a line. This is not really necessary for our example, but it might give you a better view or idea on how to generate root locus plots. Now, what I really should do is I should take 2 consecutive k values and plot a line between them. Now, this way of looping will not help me in achieving that, because I'm taking each point and basically placing a dot there or a cross there. So I should really change the for loop strategy here. And well, therefore we could do something. Something interesting. Now, for that, we could maybe create a vector that will store all the poles. And then we would then use that vector. So we should basically save all the data into a vector, first pass, and then plot it. So let me take this out. I'm not going to plot immediately. I need to place the solutions into a matrix in this case, each row being a certain pole. And then I will think about the plotting part. So I calculate these poles here. Let me call it temp poles. So these are the temporary ones. Now, if I do this, what will be the structure of my temp poles? Now you can see that it is a column vector, 3 rows, and this is just a column. So what I need to do is I should place them side by side in a matrix. So each column would be a certain k value, and each row would correspond to each pole of the closed loop. So therefore, it's quite easy to generate a matrix in Matlab. Now, how many rows do I need? I need n rows because the closed loop transfer function will have n poles. So therefore, in this case, we have 3, so let's hard code it for now. And how many columns do I need? Well, each column will correspond to a k value. So the length of the k vector would give me the number of columns. So length of kvec. Now, this on its own generates me the empty structure that I want to generate. It has 100 points because of the fact that we have this vector here, and it has 3 rows because it's a third order system. Now I need to access all the rows, but the ith column in this case, because I have already a 3-row, 1-column structure here, and this is not temp poles, this is poles. So all the rows, but the ith column should be equal to this. So I have a vector, and I'm deciding that my closed loop system is a third order one. So I need 3 rows because each row corresponds to each pole. And I have length kvec columns because each column corresponds to a certain k value. And in this for loop, I'm picking one k value, calculating the poles, and place it to its own position. So you can also place in here 1 up to 3. So this is also possible, but omitting the values gives us the same. So all the possible rows here. Now let's look at the results before we plot it. Now, if I access it like this, all the rows, but the first column, this would be my first point, and the second point would be the second column. So what I really have to do now is I need to plot a line between this complex value and this one here. And you can see it moved a bit. And the same for this and this here. So connecting the corresponding rows with a line would give me hopefully what I want. So let me copy this one here. Now I don't want to start from 1, but I want to start from the second column, because what I'm going to do is I'm going to use ith column and I minus 1th column. So 2 consecutive columns. Yeah, let's say P1. So this should be poles, all the rows, I minus 1th column, and repeat it with the next column. So P2 is the next column. So starting point and ending point, basically. P1, I will start with P1, connect to P2. But I have to cycle through the elements because I have a certain order, which is 3 in this case. So I will look for each. So let me start with this one here, by the way. I will start with each row. So take the first row of P1 connected to P2. So therefore, what we need to do is we need to change this a little bit. We need to add a certain x vector and a certain y vector. So the real value of, let's call it P1. And then the real value of P2. And let's repeat the same with imaginary values. So we have P1, P2. Let's take this imaginary part. And then I will provide x vec and y vec. Now I don't need this cross anymore. I have the color and the line. So let me run it first. If I have certain errors, we'll see. But it seems like we don't. Now, I'm not sure if you can see, but there are small lines here. I am not going to be, yeah, I did zoom in a little bit. And hope that you could have followed through. So what I'm really doing is I'm getting the columns that are next to each other, and I'm picking the P1 x point here, and then the P2 x, put it in a vector, and then P1 y and P2 y, put it in a vector and provide it to the plot. Now, if I go through all the k values, then this would be the result here. Now, of course, we have a little issue here. You can see that this point here is a special one. You can also calculate this using the root locus rules, if you remember this. And you can see that there's a certain thing going on here. And the reason behind this behavior is the lack of accuracy in our vector, because we are using 0.1 steps. So this doesn't capture the exact point where we have a coinciding pole here. So therefore, we could increase the k vector
Aralığı daraltmamız gerekmiyor mu hocam? Çünkü uzunluğu arttırırsak daha fazla gidecek sadece.
Evet, tam olarak ondan bahsediyorum. Yani buradaki hassasiyeti artırmamız gerekiyor ama aslında aralığı da arttırmamız gerekiyor. Çünkü kök eğrisi sonsuza kadar gidiyor. Yani sıfırdan başlayıp sonsuza kadar götürüyorsun vektörü. Ama bir de hassas götürmen lazım. Tam olarak ondan bahsediyorum. Now, shouldn't we increase the interval? Shouldn't we decrease the interval in order to have a better and a more exact root locus plot? Of course we do, but don't forget that the root locus gain is starting from 0 and it tends to infinity. So we should also cover the bigger values, the huge values also. But we need also a certain precision, and we are lacking that. So if I try to increase the step here, let's see if it's enough. Still not really covering it here. You could also go ahead and calculate such k values and then include them in your k vector, etc., etc., etc. But we're not really interested in that. But if I increase this up to 10, because 10 is not even a large number, it takes more and more time. And if you remember the usage of R locus, it is quite fast. So this is not ideal. I don't want to go ahead and decrease it more and more. Maybe I could also start with 0, by the way. I didn't try that one. So it's not really ideal to decrease the step here to increase the precision, because I also have to increase this k value here. And you can see I can approach the point, but I'm not really hitting it. So it's also a numerically unstable point if you have two values at the same point. So if they are coinciding, then you have numerical instabilities in this point, and you can see that on this plot. So maybe using a linear step is not a good idea in this case, because I want to have precision in low gain values, but I want to cover also higher values. So maybe instead of using this vector, I might use logarithmic space, which means that I'm increasing my step size as I'm going through the elements. And I can also choose how many points I want to generate. So let's use 200 points, start with 0.01 and end up in 1000. So this might be a better way. Let's see. And I guess it looks a little bit better. Still, we're missing the exact point, but the aim of this question is not really to have the best root locus plot that's available, but to get a basic understanding and to get to know the root locus a little bit better. So now you can also argue that the open loop positions are missing because we have just lines. There are no crosses for the open loop poles. And we can solve that by, well, if you're lazy, you might go ahead and, since we have 0, oh, we don't have 0, by the way. We have 0.01 in our k-vec. So what you can do is you can go ahead here and use, again, num-den, numerator and denominator, to extract the values out of the open loop. Now, then we will have the denominator. Let me copy and paste this code here. So here, now what we can do is we can get the coefficients. We're basically repeating the step in this for loop here, but we don't have to plug in a certain k value. Get all the s values, convert it into double, and then get the roots of this, because this will be a vector. This is called poles. Because I'm going to redefine it, it's not really a problem here. And what I really want to do is I want to, let's have 4j equals 1 up to 3. Or I don't even have to, because I don't want to really color them. So let's directly call plot, get the real values of the poles and the imaginary values of the poles, and use the color black and place an X, use also a line width of 2. So that should work because this is a vector. This is a 3x1 vector. And if I get the real part, note that Matlab functions work on vectors. So it will give me a corresponding vector with the corresponding values. So this should basically work. Let's plot it again. There you go. Now you have the open loop positions here. And then also each branch has its own color. Now, yeah, there's a problem embedded in this root locus plot algorithm. And that one is the following. We assume that each row corresponds to the actual pole that we're interested in. And this seems to be correct in Matlab for low orders, but the higher the order gets, the complicated this thing becomes, because we have a problem of assessment of which pole went where. That's called pole coloring, and it's way out of our scope for now. But it might be possible that if you try this using a different programming language that doesn't have things embedded like in Matlab, then you might take a little bit care in assigning colors to poles. We think we've assumed that it is ordered in this case, and it seems to be that, but this is not guaranteed. So this is not a perfect root locus plotting code, but it works and it gets the job done for now. Now, of course, we don't want to use this. We will use, let me create another figure. Of course, we will use the control system toolbox version, but I wanted to show and talk about the root locus plotting. I guess this would be 1, 3, and 2, and then a 0. Of course, this is figure 2, R locus. Of course, we will use this piece of code here. There's something wrong, I guess. Oh, no, it's not. Okay. Yeah, let's run this one more time. There we go. This one is generated using R locus. This one we've plotted our own. Now, hope that you have an idea about how to plot root locus, and hope that it was fruitful for you. So we've talked about the p-type controller. We've talked about the usage of the root locus, because the root locus will come up in the upcoming weeks. So this is basically part 1 here. We've talked about the part 1 part here. Now we have a part 2, which is about a Bode plot. Let's talk about a Bode plot. So yeah, let's also have some S. Let's define again a very basic transfer function. And note that this is a symbolic toolbox transfer function. Now, there are 2 questions here, again, as in the case of root locus. What is a Bode plot, and how can we generate it using the symbolic toolbox? Now, the Bode plot is actually a very important tool in control engineering. And the reason behind that is the following. We use usually the S variable, the Laplace variable here. This means that we're most of the time dealing with the Laplace transform. So if I, for example, talk about a unit step function, ut, I'm going to use 1 divided by S, because this is the time domain representation of the signal that I'm talking about, and this is the Laplace domain representation. So Laplace is very common for us. And defining systems using the Laplace transform is also common, because transfer functions are defined in the Laplace domain. But there's also the frequency domain, which is very useful, and the part 2 of our control system design course. Now, if we talk about the frequency domain, then the Fourier transform is very important, because we talk about frequencies and some gains and some phases in the frequency domain. Now, there is a relation between the Laplace transform and the Fourier transform, and it's really simple, being the following. If you look at the transform integrals, you will see that if you plug in S equals j omega, the Laplace transform becomes the Fourier transform. Therefore, if we plug in S equals j omega in our transfer function, it basically becomes a frequency domain representation, which is in the frequency domain, in the Fourier transform. So this is a special help and meaning for us, and a usage for us, because if we do such a thing, we will see that, and let me do it by the way, we can again use subs here, which substitutes. We can use GSS, this is our transfer function expression. This is the Laplace domain variable, and I want to plug in j omega, or in this case, 1i times omega. So you can do also omega times I, but I'd like to use and stick to this, because 1i is explicitly talking about square root minus 1 or the imaginary number j or I. So 1i times omega. But therefore, we need to define omega, because omega is, again, a symbolic variable. Now, if I do this, I get the following. Again, Matlab doesn't really show it in a human readable form. For a first order system, it's not really that big of a deal, but still. So now it is actually interesting, since we have 1 divided by 1 plus omega I, and this is basically a complex valued function of omega. I can plug in omega, get some complex numbers, and that's basically it. And hopefully that has a meaning. So yeah, in the Fourier transform, we talk about the gain and the phase. Now, if we have a sinusoidal, let's have one, and for example, sine of t. Now, this signal has a certain frequency, a certain gain, and a certain phase. Now, the frequency here is basically 1, omega is equal to 1. The gain is equal to 1, and the phase is equal to 0. Now, I can generalize this into this one here, sine omega t. So I can change the frequency. I can also add a certain theta and a certain gain. Now, I'm talking about transfer functions, and suddenly we have a sinusoidal. What is the connection? Now, the interesting part here is that we're dealing with linear time invariant systems, LTI systems. And this has a special meaning. First of all, if we have inputs, if we have linear combinations of inputs, then the output is expected to be the linear combination of the outputs individually. So we can use superposition, we can use this linear property, and we have time invariance. All this gives us the following. If we apply a certain sine wave to the transfer function, so we have this transfer function, we have an input, and we have an output. If we choose u as sine omega t, and then the output, interestingly, is again a sinusoidal wave. It's still sine. And if you're familiar with the frequency domain, then you would know that the frequency only changes if the sources change, or the frequency of the source changes. So it's only source dependent. So that means that whatever the sinusoidal in the output is, it will be something like this. It will have the same frequency. So this is an important property, but we don't guarantee that it will have the same gain or phase properties. That's not guaranteed. The only thing that will not change is omega, which is the frequency of the output. So you can also use some complex looking input signals. You can decompose them using the Fourier series. So basically each signal, or all the signals, can be expressed in terms of sinusoidals and their combinations. So therefore, analyzing each frequency for a transfer function is really important. So how can we determine the output gain and phase, so A and theta, using the transfer function itself? So is it possible? Now, one way, and this way is basically an experimental way, is to sit in the lab, connect a signal generator, generate some sinusoidals, apply it to the system, observe the output, and look at the phase and gain differences, and prepare a plot, for example. There's another method that we can use, and which will be the case in this case here, is to use a transfer function itself, because the data is hidden in the transfer function. Now, since we have something like this, it does not seem very helpful if we stay in the Cartesian coordinates. But if we change it into polar coordinates, we will see that the transfer function will have a certain gain and a certain phase. And how do we calculate this? Well, we take the real part, the imaginary part. So take the real part of g omega, take the square plus the imaginary part of g omega squared, and then the square root of this. Now you can see that this will be basically a function of omega, and that's it. And the same applies here. We will have a tan of imaginary of g omega divided by the real part of g omega. So this will also be, again, a function of omega. Now, this helps us to determine what the output will look like. So this helps us for a certain frequency. I can tell the following. I can say that at this frequency, applying a sine wave with gain 1 and phase 0, I will get the following gain and phase properties with the same frequency. Namely, the gain is calculated using this, and the phase is calculated using this. So this basically means that the transfer function itself gives us the properties of each frequency and the behavior at that frequency. I can say that the sine wave will be amplified or attenuated, and the phase will be shifted this much. So I can really examine the system and find out its behavior properties. So let me show you an example. So I will come back to this. Let me comment it out. Now, let's run this. Not this one. Let's run this. Now, we have g omega, the real part of g omega. Now, of course, I need to tell the symbolic toolbox that omega is not a complex value, because by definition, it's a real value and a positive one. If we define symbolic as symbolic omega like in line 3 and 6, then it will automatically take the most general case, so it can assume it to be a complex number. But if I append this real here, it means that this will not be a complex number. So I'm basically having a protocol here, and I'm telling that omega will not have a imaginary part. So if I take the conjugate of omega, it will give me omega. If I take the conjugate of s, then it stays as conjugate s because it can be a complex number. And in this case, s is a complex number. So therefore, we have a little difference here. So if I do this, hopefully, this will help me in calculating it. But, so what is the problem here? Not enough input arguments. Oh, there's a typo. Okay. So there we go. Now we can see that this is going to be the gain, and then we will have a certain phase angle coming from this. So we can also use a tan d to generate degrees. That has more meaning for us. So let's try one value. Let's say the omega value should be equal to 1. So this means that I will apply sine t. And the output should look like this. So what I can do is I can calculate these values by using subs. So let's take this. So let's say gain val is equal to double subs. I'm converting into double because I'm going to plug in all the unknowns. So into the gain, instead of using omega, use omega val. So I'm going to do the same here for the phase value. Instead of gain, we will use phase. So gain val looks like this, and phase val looks like this. This means that if I use an input u equals sine t, then my output should be 0.0 707 sine t minus 45 degrees. That's it. Of course, let me also tell you that this will not be the case for the transients. So this should be in the steady state. So that should be noted. But other than that, this will be the output. So let's test this. And we can test it by using a function called Lsim, which is a linear simulation function. It will give me the output that I'm looking for. And I need certain parameters, namely the time vector. So let's have 10 seconds. And I'm providing sine t. And I also need the transfer function. Again, if you don't recall, you can always go ahead and ask for Matlab, and it will say that you need a certain transfer function, an input, and a time vector. And it will generate the output. It will simulate the response of the dynamic system. So since this is a basic system, we've defined that, and the usage is GSU, T. So let's run this again. It seems like we have our output here. So let me just quickly copy this here. X label should be time, and this should be basically output. So let's plot this. Now t comma u, which is basically the input here. Let me also have line width 2. And the output, which is basically blue. And yeah, let's also say that this is sine of t, and then this is 0.707, or let's make it more general. So now you can see I have basically plotted the input and output, and you can see that the peak value here is approximately 707. That's not the case here because this is still in the transients, but here somewhere you will see that it will stick to that. It will become 707. This is a bit higher because there are transients, and this only holds for steady state. So up to some point here, it will behave a little bit different, but then it will settle down to the steady state. So we can increase the time here and see what happens. Now, this might not seem that useful, but hold on. If we change the frequency, it will be a different thing. So let me include the frequency here so that it'll be updating. So let me increase the frequency a little bit. Not this one. So you can see now that for high frequency, we have this frequency increased. That's nice. But what we can also see that is that the output has a significant drop in gain. So we can assume that for frequencies 10 radians per second, that the output becomes attenuated. So if this is for example, if this is a transfer function, and if I have noise that has this exact frequency, then I would expect that the noise will be attenuated like this. And if I increase this, it will become more and more attenuated. And the reason behind that is that this is a special transfer function. You can see we have a really high frequency, but we can see that attenuation is also very, very high. But this is not the case in low frequencies. For example, 1, but let's also have 0.2. So we can see that it's almost the same, a little bit of a phase difference, but the gain seems to be the same. We're still in the transients, but yeah. Now, using this small analysis, I can conclude that this system is a low-pass system, low-pass filter, because in the low frequencies, it does not really attenuate that much, but in the high frequency ranges, it has a high attenuation. Now, how can I judge the attenuation of the system by looking at a graph? Well, you can use this sinusoidal wave approach, but you should use basically the body plot, because the body plot helps you in understanding how the system will behave in the frequency range. So you can pick one frequency or working frequency, and you can see what the output will look like. Now, instead of calculating this stuff here, let's try to plot the body plot. Now, for that, as it was the case for the root locus, we need a vector for omega. Now, let's directly pick log space because we've already seen it. The reason why we will use logarithmic space or log space in this case is that we will look for low frequency regions, mid frequency and high frequency regions in one plot. We want to combine them. And the log space is suited for this. If I have linear spacing, it will cost me some CPU performance, etc., etc. Now, I will again repeat the same. I will pick each element, and using each element, I will go ahead and calculate certain gain and phase values. Now, let's call this gain function and phase function. I've talked about this, but let me repeat myself. You can use this and then gain val, comma, to generate a vector. But this is not really efficient, but this is easy to code. This should be val. So if you're not really confident, then you should use this. Once you get used to it, you should opt to the following. Since I know how many elements omega vector has, and since I will use this omega vector for each omega calculation, each iteration, and the results will be stored somewhere, I need the same structure, but with zeros. So the easiest way would be something like this. I can also do that, but I'm not going to. Let me show you. You can also do something like this. So 0 times omega vec should be, for example, gain. So it's possible to code it like this, but I would prefer to do the following. Let's use zeros, which will allocate me a vector of zeros. And let's use the size of omega vec, and that's it. So this is a shallow copy in some sense. It does check for the size of omega vec. Whatever that size is, it will use the same size and generate a new vector out of it. So this seems to be self-explanatory. Therefore, I like to use that. And I generate a phase vector. Now, from this point on, I can use omega vec length here. And instead of growing a vector, which is computationally inefficient, I'm going to just index the variable that is pre-allocated, basically. So I'm using the gain function and phase function. I'm plugging in omega val into omega. So therefore, the omega val should be picked from the omega vector. So before we plot anything, let's run this code and see if it runs properly. So if I say gain, we have a certain gain. If I have phase, we have a certain phase, and there's omega vec. So the only thing left here is to prepare a nice plot that explains this stuff to us. Since we have an omega vector, and we have two additional vectors, we will use one plot for gain, because this will be gain versus omega, and then another plot phase versus omega, but we will align them so that we can choose an omega value and trace its gain and phase simultaneously. So therefore, let me create the following. So let's have two rows, one column, and the first of this here. You can also save the current axis here, and GCA stands for get current axis. So this is one axis, and if I copy this, I will create another axis. So the plot area is called axis in this case. And this will be the second one. Of course, the x-axis is omega. Here we will have, so let me have a more mathematical notation here. So we will have something like this here, the absolute value of that. And then we will have the arguments or the phase of this here. Of course, this should be the second one. So you can use these handles here, down here, to plot on a specific plot. So that's the nice thing about that. For example, I want to use the first axis. I want to plot on AX1, and I want to use omega vec as the x-axis values and gain for the y-axis values. And let me also, again, provide the line width of 2. Maybe let's also use black here as a color. So let's repeat that for AX2 and also phase. There we go. There's a comma missing here. Now, let me, by the way, close the second one. So, yeah, this is a body plot. Even though it doesn't seem like one, it's still a body plot. Now, the traditional look is a bit different. And the reason behind that is that we've used, for example, omega vec in line 16, as you can see here. We've generated it using log space. But if you look at the x-axis, you can see that the steps are not really logarithmic. They're just linearly spaced. So we have to change that. We have to change the way that Matlab plots its or chooses its x values. So for that, we need a workaround, and that workaround is used using set and get functions. So we will provide the current axis. You can also provide AX1 and set the x scale function, so the scaling function, to log. Because now, if we look at get AX1 and look at x scale, you will see that it is linear, but we want to have logarithmic, so log. So we'll change it manually to log. So run 2. Let's try it again. Now you see the more traditional, it has the look and feel. Now, yeah, this is basically it. But the body function from the control system toolbox has just one difference, that being the y-axis values here. If we use 20 log j omega, then we will get decibels, but here it's not decibels. That's the only difference that is left. But other than that, I can see that the low frequency region has high gain value, almost equal to 1 or equal to 1. This means that signals applied with these frequencies will pass through without loss of any gain. A slight phase shift starts here somewhere, but at this frequency, we have the corner frequency of this sort of filter or transfer function. And then it starts to drop down in gain, and also the phase difference becomes larger and larger. And at some point, signals are attenuated or rejected at this point because it's equal to 0. So the body plot helps us in understanding the behavior of transfer function systems, which is the point of control, because in control system design, we aim to change the behavior of systems. So we need, for example, the body plot to understand how it's going to behave. So it's basically an important plot that we use a lot. So, of course, you can use the body plot itself. We don't really have to go through this stuff here. The body plot on its own gives us the necessary values here. We can call body, as it is the case in the step function. So let's define this. So if we use it like this, let me also add a little piece that is squeeze. So the squeeze will get rid of extra dimensions because the body plot is not really meant for only single input, single output systems. You might have multi-input, multi-output systems. In that case, the body plot will generate you a multi-input, multi-output magnitude and phase vectors, and it will have an extra dimension in order to determine which input channel or between which input channel and output channel this body plot is generated. So therefore, in our case, we will use systems, so we will just get rid of the extra dimensions, which are not really necessary in this case. So with this small piece of code, you can skip the whole calculating from scratch part here, but you can use the same plots here. So combining these lines of code, you can generate the same exact body plot. Now, this will have some advantages when we cover the frequency domain methods, because we can annotate and manipulate the data that is already calculated into mag and phase. So let me show what mag has, what phase has. So you have basically frequency, phase, and magnitude. You have everything you want from a body plot. If you omit that and just call body, it will generate you the plot. So let me also do that to compare with our plot. Now you can see this one was generated, this one was generated by us. There are some minor scale differences. It is stopping at minus 90 degrees. We stop at minus 100 degrees, but we have a higher frequency range. Therefore, we can change it to minus 2 and 2, and it will become the exact same. So, yeah, this also concludes the second part here. We have a small bit left for today, and then we'll conclude the lesson of today.
Geçmeden bir şey sorabilir miyim?
Tabii ki.
Bu squeeze fonksiyonlarının ne yaptığını bir tekrarlayabilir misiniz bir defa daha?
Squeeze fonksiyonu bizim için aslında çok önemli olan bir fonksiyon değil. Ekstra boyutları yok ediyor. Şöyle göstereyim. Şöyle çağırdığımız zaman, magnitude'a baktığımız zaman 2 nokta üst üste virgül, 2 nokta üst üste virgül 47 diyor. Şimdi burada aslında işte birinci giriş, birinci çıkış arasındaki 34. eleman şeklinde burada magnitude oluşturulmuş. Ama biz squeeze dersek bu yapı ortadan kalkıyor. Direkt bir vektör veriyor. Ve biz genellikle tek giriş tek çıkış kullanacağımız için dersin içerisinde otomatikman squeeze yapıyoruz. Aslında onu yapmadan şöyle de yapabiliyoruz ama o notasyon belki kafa karıştırır diye yapmadım. Şöyle bir şey yapınca da oluyor. Magnitude eşittir magnitude yapıyor aslında burada. Şunu kaldırayım. Şöyle miydi? Muallak parantez miydi? Benim de kafam karıştırıyormuş. Şöyle olması lazım. Heh. Aynı işlevi görüyor. Yani ekstra bir boyut ekliyor. Dediğim gibi MIMO sistemlerde bir giriş bir çıkış olmadığı için, daha fazla giriş ve çıkış olduğu için hangi giriş çıkış arasındaki body'yi istediğimize göre değişiyor. Onu da komple bir şeyde tutuyor. Yapıda tutuyor. Biz o yapıdan kurtuluyoruz squeeze'den. Now the question was on the usage of squeeze. Why do we use it, or what does it really do? Now, as I've tried to explain, the body function works also on MIMO transfer function matrices. So multiple inputs and multiple outputs. This means that we will have several channels. So I can be interested in the behavior between the first input and, let's say, the second output. So therefore, the mag and phase variables here might have an extra dimension that helps me out in choosing the right input channel and right output channel. And as you can see in this case, if I type in mag, I can see that there are 2 dimensions used for input-output channels, and then there's a third dimension which has the actual element and the vector value in it. So in order to get rid of it, I can use this approach, which gets rid of this structure, because there's no really need for a single input, single output systems. Or you might also use squeeze, so it will get rid of the extra space. So it squeezes it down to a 1D vector. So, yeah, that's pretty much it. Now, the last bit is about the impulse, step, and ramp response of a certain system. Now, here we won't use the symbolic toolbox anymore, which we could, but I omitted that part. You can use the inverse Laplace transform here in order to calculate system responses, but yeah, it doesn't help that much. So we will stick with that. But the aim here is the following. We know the step function. There is a function called step that will automatically generate the step response of a certain transfer function. What about using the same step function for impulse and ramp responses, or even parabolic inputs? So is it possible to use the step function, but adapt small things about the transfer function, or update small things of the transfer function to end up in the impulse or ramp response? So obviously, if I'm trying to do that, it is possible. And I wanted to talk about another aspect of LTI systems and to show how to calculate impulse and ramp response. So as far as I know, there's no ramp function, but there might be an impulse function. So this ramp is not found, but you have step. I'm not sure if there's impulse. Let's also look for that. It seems like we have impulse, but we don't have ramp or parabolic input. So we can do that on our own. And let's see how. So let me again define our transfer function of the day, which is 1 divided by s plus 1. So if I use this, so run 3, we will have y, we will have t, and this is basically the step response. So let me maybe take this. There we go. So this is, we don't even need any y label. Let's say that this is t. And there we go. So now I'm going to plot on AX1, t comma y, line width 2, and that's it. So this is the step function. It calculates the step response of GS. Now what I want to do is I want to use again the step function, but a little bit different so that I will get the ramp response, the impulse response, etc. So how is this possible? In order to understand this, what we have to do is we have to focus on the step function. Now, if I'm talking about a transfer function, I'm talking about the Laplace representation of the relation between input and output, which is in our case 1 divided by s plus 1. So if we use the relation here, I can see that by using line 8, I'm basically calculating output. Now, I've talked about the unit step function. If I'm talking about step, its meaning is that I'm talking about the unit step function. Now, this function has a Laplace domain representation, which is 1 divided by s. So if I'm interested in the step response, I might go ahead and plug in 1 divided by s, which would give me, for example, this. Or you can also write this here. So the only thing left would be to take the inverse Laplace, and it would give me a time domain expression. I would plug in a time vector, and that would be my step response. But since I want to, for example, use the impulse response, then the strategy changes. Then, now let's say that this is step response. So this is the step response. So what if I want to use the impulse response? I want to calculate the impulse response. So then, so basically US, let's call it US. So I said that for the step response, I'm using this. So let's put it in here. So I've plugged in U equals 1 divided by S, and I got at this. So what if I want to calculate the impulse response? Well, then the Laplace transform of its delta t, so the Laplace transform of this is basically 1. So instead of plugging 1 divided by S, what I have to do is I should plug in 1, because that's the Laplace transform of unit impulse. So this means that I should take the inverse Laplace of this. Now, what I'm suggesting is that instead of doing this, I want to come up with a different transfer function, and I want to use the step function. So it should be 1 divided by S. And if I call step HS, it should correspond to the impulse response of GS. So basically, I'm interested in this. Instead of calling some other function that calculates the impulse response of GS, I want to generate another transfer function that will give me basically the impulse response of GS. So since these should be equal to each other, this means that I'm talking about HS divided by S should be equal to GS. So this would give me S times GS. So my suggestion is that instead of using step GS, I might go ahead and use S times GS, and that will correspond to impulse response. So what I also think about is that if I want to have the ramp response, I can repeat the step. I can go ahead and look at this. This is basically GS. But this should be basically GS divided by S squared, because the inverse Laplace transform of this would give me the ramp response. But I want to come up with a transfer function that will give me the ramp response. Now here, it is obvious that HS should be equal to GS divided by S. So the reason behind this is the following. I provide a S times GS, and in the Laplace domain, this will be multiplied with 1 divided by S. So S will be canceled out, and it will basically correspond to the inverse Laplace transform of GS. Here, the same, I provide GS divided by S, and the step function behind the scenes will add another 1 divided by S. So I will end up in GS divided by S squared, and the inverse Laplace transform of that will correspond to the ramp response. And I can go on like this. I can use, for example, GS divided by S squared in order to calculate the parabolic input response here. And the reason behind this is, again, that we are dealing with linear time invariant transfer functions. So if I take the derivative of the input, I might also, and I will also get the derivative of the output. If I provide the integral of an input, the output will also be the integral. So therefore, I can take the derivative of the transfer function, and use the step, so it will give me basically impulse, because times S means taking the derivative. So I'm basically embedding a derivative in there that will take the derivative of the input or the output. So this little hack sort of will help me in generating all the necessary stuff that I'm after. So for example, I can do this times TF. And since I want to take the derivative, oh, this is the ramp, I want to add an integrator, and that's basically it. So the impulse should be including a derivative. Let's get rid of everything here. So let's also have a 3-row, 1-column plotting here. Let's give it a title. This should be impulse. So let's copy this. This should be step. This should be ramp. 2, 3, and again. There we go. So this is impulse, impulse, ramp, and ramp. There we go. Of course, what we can do is we can also try to plot the input signals. Of course, it has no meaning to try to plot the impulse type input because it's just one impulse at 0 with infinite magnitude. Or you can also use the unit impulse, which is a 1 magnitude impulse. But yeah, it's not really that meaningful. But we can plot the unit step function and the unit ramp function in order to compare the input and output. So for that, what we can do is we can go ahead and do the following. Now we should plot once, and let's give it a color. Okay, let's make it blue here. And there we go. So there we go. Now, instead of using 1, this should have equal size. What I can do is I can again copy the size of t and generate a vector with 1s in it. And here, I don't really have to do much. I can just go ahead and use tr and tr because unit ramp is y equals x or y equals t. So let's have that. And there we go. Now, of course, here in the unit ramp, it's not really that easy to see. You have to zoom in to see that there are 2 vectors. In such cases, you might increase the line width of the reference signal here. Then you can see that they are on top of each other. So yeah. Now it is possible to use the step function in order to generate the impulse response, the ramp response. Only thing that you have to do is to add some integrator or derivative action based on the response that you're after. Now, before I conclude the lesson, let me show you the notes that I've prepared for this week. There might be little slight differences because I'm not looking at this PDF during the lecture itself. So here you will find basically the same main points, but maybe some slight differences may occur. And you can see that I have talked about in the root locus plot, you have the code here that will basically generate to you the root locus plot. But I have also talked about the second order transfer function that looks like this, which has some importance for us. Here we have special parameters called zeta and omega n, zeta being the damping ratio, omega n being the natural frequency. These have special meanings for us. We will talk about them in the upcoming weeks. But yeah, any second order transfer function without any 0 in the numerator can be determined or can be characterized by zeta and omega n. Looking at these 2 parameters, we can determine how the second order transfer function will behave. Will it overshoot? What settling time will it have? Etc. etc. Can be determined based on zeta and omega n. And the source of this zeta omega n usage is basically the second order polynomial roots. So the way you calculate that. If you remember, if the coefficients are a, b, and c, b squared minus 4ac is the discriminant, and you can see what if the poles will be complex conjugate poles, if they will be coinciding, or if they will be distinct real values. So that changes the behavior of the second order system, and zeta is basically that, because you can see that instead of b squared minus 4ac, we have 1 minus zeta squared and the square root of that. So this will help us in determining the behavior of a second order transfer function. If you're not really familiar with this whole zeta omega n stuff, then you might look at the notes and try to solve, for example, the roots of such an equation. And then we will talk about this, but you might also experiment with zeta and omega n. But as if I'm not wrong, we will take this into consideration. So yeah, and there are special plots on the S domain, because if zeta is constant, then we have something. If omega n, the natural frequency, is constant, then we will have another thing. So there are zeta and omega n lines, they are called that, and you can see an example here. If omega n is, for example, constant, you will have this circles here. And if zeta is constant, then you will have these linear plots here. And if they coincide, for example, for this point, we will have a conjugate pole, and that will correspond to a certain second order transfer function. Yeah. Now on the root locus, we use these grids here to choose certain characteristics, but in this lesson, we've talked about the stability aspect of the root locus, but it's also possible to try to come up with transient properties. So in the frequency domain example, in the body graph, body plot example, I've chosen a bandpass filter because that's quite interesting to analyze. And it has bandwidth, which will be obvious if we look at the body plot itself. This is the bandwidth, basically. And then we have some quality factor. Again, this determines this width here. If we want to specifically pass the frequency 100 Hertz in this case, then you have to increase your quality factor to have a narrow band around here, because in this case, it's not only passing 100 Hertz, but the neighbor frequencies are also passed through this filter. So there are certain aspects like that, but that's not really the point of our discussion here. But it is interesting to see that a certain bandpass filter can be expressed as a second order transfer function. If you look at this transfer function, you wouldn't directly conclude that this is a bandpass filter, but if you use the body plot, and I've generated the symbolic expression for it, substituted s equals j omega, and all that stuff that we've covered so far, you can do that on your own, and you can see that this will be the behavior of the transfer function, which is, interestingly, a bandpass filter with a bandpass frequency 100 Hertz. So yeah, this is basically a different example, as I talked about. You can change the quality factor, etc., to see what's really going on. And you can see that set dca x scale log is also written here. And the last part, the third part of today, was to use the sub function for different type of inputs. You can see that actually we're interested in gs divided by s, but we can come up with another transfer function, g tilde, for example, and it can help us in determining the impulse response, the ramp response, etc. So this concludes our today's discussion. You can see that this is basically the same result that we've had here. Probably the transfer function is a bit different, or the scale is a bit different, but this is basically it. I will upload this PDF file and also today's video